Good afternoon, ladies and gentlemen of Precalculus. Welcome again to room 15 where
Learning never ends.
learning never ends, even if we have a few people missing. But we'll try to get by here. Now, what we're embarking upon today is section 4.2 in our book. We just finished up, as of yesterday, section 4.1. And before we go over, start launching into this these quick review exercises, I want to just briefly review the major things that were covered in section 4.1 in our book. Do you remember what those are? The three major things we covered, which are what?
Circles.
Well, circles, and specifically the radians to degrees to radians, and arc length formula, right? So those are two major things: arc length formula, radians to degrees to radians, and one more thing. No, that's section. That's chapter 8. Okay, that's chapter 8. Okay, the only thing is DMS, right? Degrees, minutes, seconds. Right. So those are the three major things that we covered in 4.1. I don't think they're that hard, but they're things that we're going to use a lot, and they're going to be tested. So, but should be pretty easy. Remember how to find the perimeter of a sector, right? The pizza slice. Remember how to do that. And so now we go into section 4.2, and these are warm-up exercises for that. So today we're going to spend like the first half of class doing these 10 problems, and then the last half of class we're going to talk about the meat, introduce the meat of emphasis, what 4.2 is going to be over, which is very much a building block section as well. Okay, so the thing you need to remember is the Pythagorean Theorem, and I want to show you one thing that's going to be very helpful to you is this little thing right here, your formula chart. And not everything is on this formula chart, but most of it is, and the ones that aren't here, we're going to be able to work around those with memory aid devices and things like that, okay? So the thing we need to remember for Pythagorean Theorem is a squared plus b squared equals c squared. But c squared minus a squared equals b squared. A squared plus b squared equals c squared. The c squared minus a squared equals b squared, b squared. That's right. Good job. So basically 1 and 2 are a squared plus b squared equals c squared, and 3 and 4 are, but c squared minus a squared equals b squared. So go ahead and do those, or you need me to do those, let me know. I can work them out. One of these ends up being like a 3, 4, 5 right triangle. We can talk about that in a minute. I want to point something out on one of these, which is on number 3. So you have c squared, in this case c squared is equal to 10 squared. A squared is equal to 8 squared. So you have, and b squared is question mark, but c squared minus a squared equals b squared. So you get here 100 minus 64 equals b squared. So b squared is equal to 36. So b is equal to, we'd say plus or minus 6, but is it really plus or minus 6? No, why not? You're not going to usually have negative distance, right? So we'll just leave this as plus 6. And what kind of triangle do we call this? A what? A right triangle. What other name do we have for it? This is the type of triangle we call a 3, 4, 5 right triangle. Does that make any sense? Okay, there's a type of right triangle. It's called a 3, 4, 5 right triangle. And what it is this: that if you have the legs of a right triangle whose dimensions are 3 and 4, we know the hypotenuse of that right triangle is 5. Now in this case, this is not strictly a 3, 4, 5 right triangle, but what about it? How does it relate to a 3, 4, 5 right triangle? Yeah, it's a scaled version, and Steve-O has it right, doubled, right? This is what's called a Pythagorean triple, and there's another. So this is the most common Pythagorean triple. Anybody know of any other Pythagorean triples? I'll show you what they are. I'll show you a couple more. Okay. What it is, there's another Pythagorean triple that's going to be, if you have this side here be 5, this side be 12, what's this side here going to be? 13. And then there's one more that is less common. These are the most common right here. And so I want these to be part of your geometry fluency, right? We have, let me see, another one is another one here. If you have this right triangle with this side here being 7 and this side being 24, what's going to be the dimension of the hypotenuse? 25. So, especially try to have these first two remembered well. Right? This one, and then there are other Pythagorean triples that are with bigger numbers than that even, but not. So, next, you should have, for this one here, you should have x is equal to square root of 12. Is that what you got for that one? You should have got square root of 12. How'd you get that? 4 squared is 16. 2 squared is 4. 16 minus 4 is 12. Square root of 12, well, that's going to be x, right? So you'll be able to do these in your head. And when it comes to 5 and 6, you're converting units here. What do we have to remember for this one? 1 foot has how many inches? So this 1 foot equals 12 inches. This is our conversion factor. And you can use dimensional analysis to multiply this, to set this up and cancel inches and be left with, cancel feet and be left with inches. So you should get what for this? .8, 100.8. This one here, feet to miles. We've talked about feet to miles. I had a student in third period class who said that this actually earned her a sucker, remembering how many feet are in a mile, which we've talked about recently in this class, right? Jace helped her. And she said it helped her because we've gone over this recently, right? So you're going to get point something miles is what you're going to get. Okay? And then the last four are little solution things, solving for problems. This one here, you can like cross multiply the 20.4 over here. The ones here like this one here, the way I would do this one is I would just rewrite this one to make the arithmetic a little easier. So I'd write that as B over 23.9 feet is equal to 1 over 1.72. And then how would you solve this one now? Cross multiply. So I want you to just take some minute, help each other out, finish this up. Cross multiply and divide is how I do it. Right? And you can do similarly with problem 10. Trying to see what's on this sweatshirt here.
Oh, it's Dwight Schrute
Who's that?
from the office.
Oh, okay, I'm not familiar with that.
That's the way.
He's the one that
Oh, I have seen that actor before though, yeah. All right,
Oh, yeah.
very good.
the most young man.
What I'm going to do, I'll show you the answers here. Check the answers. Here. So check your answer with Ben. He has the book. Yeah, one thing about you, one reason these exercises are set up in this the way they are for a reason. And one thing you're going to have is you can have numbers that are unitless, and that's what 9 and 10 show you, right? So you can have unitless numbers. 9 and 10, you have unit list. You have unit list numbers for 9 and 10.
What is 10?
Yeah, you should get 4 point something for 10. So JV's not playing today? Does JV play today? No?
Girls are, I mean, we lost to them last time, but we looked at it great. But I'm sure
So is everybody finished by now? Some people are. So let's try to finish this up. Then I want you to get ready to take some notes on where we're headed next.
Okay, wait, I was,
Everything but that.
wait.
That was me back then. Because I bring them all up in the calculations. Yeah, you have to get what was that? I think it's Mount Top. He's like this. Oh, he's banking this one, bro. I didn't know that. So he was he was actually the fourth or that was only 5 on top. He was a lot further than me.
Yeah, I don't know.
The biggest he's done 18.
7.91.
Did your mom knew the code?
I'm all good. I just had a day for sadness. Oh wait, 9.2.
Steve. Daddy Steve.
Big. Birthday friends.
Thank you, ladies and gentlemen. Appreciate you doing that. Luke. I need you in here for now.
The babies are us.
You should have gone during the exercise. Okay. Okay. Yeah, Luke was on his way out. This is this important piece of instruction, so I need you here for a while. Okay, we're launching into section 4.2. We're going to cover some basic things today that are really like building block important things. So we gotta be paying attention here. Okay, so this is a sketch of your basic right triangle. And what this drawing does, it gives you the anatomy of what are the building blocks or trigonometric ratios. So what you have is, doesn't have it here, but this is a right triangle. And if you have an angle, in this case indicated by this theta symbol, if you go over on the opposite side of this right triangle, you will have the opposite side. And a lot of times you'll see this like abbreviated like OPP. And then the remaining leg of the triangle down below here is called the adjacent side. And that you'll see that identified as ADJ. And then your long side is going to be the hypotenuse, and sometimes you'll see it abbreviated as HYP. Okay? You have questions about this? Okay? Well, I had a good question from third period class. What if, instead of theta being here, let's say we block that out, what if theta is over here in this corner? What do we have in this case?
The opposite and the adjacent switch.
Yeah, so in this case, so CV is right. In this case, when we have, now basically when you draw the triangle yourself, I usually just draw the triangle in this orientation that the sketch originally has. And what's a reason for drawing, gentlemen? What's a reason for drawing the triangle in this orientation, the way the book gives this figure? What's a reason for it? Okay, well, it could be. The basic, there are different things. Well, the first thing I can think of is if you look at all these, you see all these posters over here of these triangles and these circles? Like this one up here that has terminal side, this one right here. So by convention is that your angle is going to start out with the initial side it calls right here horizontally. So your angle is going to be this elevated portion here, this ray that elevates here. That's going to form your angle. So that's kind of a standard thing. Another thing is it's going to help you for a certain trigonometric ratio, which we're going to go over pretty soon. Okay, now, do you have questions about this? All right, so building blocks. So next we get into the trigonometric functions. I like to call them, instead of trigonometric functions, they are functions, but I like to call them trigonometric ratios. Why do I like to call these trigonometric ratios as opposed to trigonometric functions? Because they are functions of ratios. Now in this case, what happens is if we go back to our drawing here, we have our sine is our ratio of our opposite to our hypotenuse. The cosine is the ratio of the adjacent to the hypotenuse, and the tangent is the ratio of the opposite to the adjacent. And then, in addition to those three standard trigonometric ratios, we're introduced to three others that you probably may not be acquainted with yet. The secant theta, cosecant theta, secant theta, and cotangent theta. And all these three ones on the right these are reciprocals of these three on the left building block we will call trigonometric ratios. Now, what is it that you can use to help you remember what these trigonometric ratios are?
You write it down.
Pardon me?
You write it down.
You could write it down and remember, exactly. What I'm going to do is I'm going to go ahead and tell you my favorite mnemonic device to help remember which ratios are which. You know what a mnemonic device is, right? It's like SOHCAHTOA, right? SOHCAHTOA is probably your most famous. SOHCAHTOA, while is probably the most famous one. If you want to use that, by all means use that. The thing that I like to use is one that has a little more edginess to it. And what it is, it's called this one. Some Old Hippie. And some of you are saying it now. Caught another hippie.
Oh, yeah.
And what did that hippie catch the other hippie doing? Tripping on acid. Tripping on acid. So what we have for sine theta is going to be equal to our opposite over hypotenuse. Some old hippie caught another hippie is going to be cosine theta equals adjacent over hypotenuse. And finally, your tangent theta, which you usually see abbreviated TAN, is equal to our opposite over adjacent. And so those are your three building block trigonometric ratios. In addition to those ratios, we're introduced to a new set of three, which are called the reciprocal trigonometric ratios. Now, if you go to your ACP formula chart right here, you're going to see those ratios the way they're listed here. And they're kind of listed on your formula chart as pairs. So it shows you that your cosecant is your reciprocal of sine. So that means that sine is going to be the same as 1 over cosecant, and cosecant is equals 1 over sine. They are reciprocals of each other, right? Reciprocal of pairs. You multiply the cosecant and the sine of an angle together, they will be 1. Similarly for cosine theta and secant theta, and likewise for tangent theta and cotangent theta. So again, the reciprocals are going to be CSC theta equals hypotenuse over opposite, secant theta equals hypotenuse over adjacent, and finally cotangent theta is equal adjacent over opposite. Is it going to be hard for you to remember those things? Maybe, maybe not, right? But are you going to be able to figure it out if you momentarily forget for some reason?
There's no way to put those in the calculator.
Yeah, okay, that's a good question. Okay, now, if you have the calculator here that John likes to use, the TI Inspire, the TI Inspire actually does have those different trigonometric ratios. Although it's not, let's see if this is charged up here. I probably need to charge it. I'm going to have to charge this one. But the TI Inspire has all 6 trigonometric ratios. You go over to the left. I'm going to show Kim if it comes up here. Okay. This one here. Oh, there it is. Okay, yeah, it has some power in it. Okay. So Kim, if you go over to the trig button like this, you see them all listed here. Right. But you have a sine, cosine, and tangent button on here, so I'll just see what the TI Inspire looks like. So you press the trig button, you have this kind of sub-menu out of it. And you don't have that on your TI-84 series calculator.
No.
So what you'll do for that, to put this in the calculator, if I want to see what the cosecant is, the cosecant of 30 degrees, I'm going to go ahead and put the cosecant of 30 degrees. I'm going to do it like this. I'm going to put 1 over sine of 30 degrees. Does that make sense? And so, making sure I'm in degrees, right? We've got to make sure we're in the same. So 1 over sine 30 degrees is 2, which is what the cosecant of 30 degrees is. So if you just enter the reciprocal of that trigonometric ratio, you'll get what you're looking for there. Does that make sense? Is that helpful to look at? And it's on your ACP formula chart what they are too. They're right here. You can see right here in the middle, they have what the reciprocal ratios are. So you have access to that. Let's look at isosceles right triangle. This one here is a 45, 45, 90 right triangle. And if you have this side here, you go to your ACP formula chart, and what you have is, look at special right triangles for 45, 45, 90. It says x squared root of 2. So in this case, if our hypotenuse is 1, we're going to call that x squared root of 2. And this will be x here, and this will be x. So if we say 1 is equal to x squared root of 2, then x is going to be equal to 1 over square root of 2. And then we can rationalize this by multiplying this by square root of 2 over square root of 2. So we're going to get for this one square root of 2 over 2. You remember the unit circle trigonometry song? The x's are 1 square root of 3 over 2 horizontal. They must be square root of 2 over 2. Right, square root of 2 over 2. And next are 1 half and 0. This be x. Okay. And then for the sine, 0, 1 half and square root of 2 over 2. That's what I'm telling you. Square root of 3 over 2 and 1. The sine is the height at any radian. The square root of 4 over 2 is 1. Good job. 0, 34, 5, 16, 19. That's why I would circle trigonometry. So anyway, all embedded. And again, a song like this one we sing is also another type of mnemonic device, isn't it? Okay, and then we have this type of triangle, which is called a 30, 60, 90 right triangle. And for this one right here in our formula chart, we have this one right here. Thank you, John. We have this one right here. Yeah, we have this one right here. X squared root of 3 and 2x. So this one will be x, 2x, and here's x squared root of 3. And we can find out what they are if we want to solve for these different sides. So we have 2x is equal to 1. So x is equal to 1/2. And then x squared root of 3 is going to be equal to square root of 3 over 2. Okay? So this side will be square root of 3 over 2. This side will be 1/2, and this side here will be 1. So just some things to kind of keep track of. Questions on that one? Okay, just a couple little things more. Just about finished today. I'm talking a lot today. Okay, how to create a acute angle theta such that sine theta equals 5 over 6. And so here we have, in this case, we have our opposite side being equal to 5, and our hypotenuse is 6. So what we say is, we say that sine theta equals 5/6. Just a minute. I'll send you out pretty soon. Okay, 5/6, and cosine theta is equal to x/6. And if you know what theta is, you'd be able to solve for x, right? And then this one right here, we have an example problem. We want to solve for side A. How do we do that? Yeah, so sine of this angle, which is 37 degrees, is equal to our opposite, which is A, over our hypotenuse. So what is A equal to? 8 sine 37 degrees, right? And then what is B equal to? Okay, this is going to be your adjacent side, right? So B is going to be equal to 8 cosine 37 degrees. Because, why is that? Because cosine 37 degrees is equal to B over 8. Okay, so that's where that comes from. Okay, this one here, I think the last one I'm going to have us look at today is this one here. You have a building, and this might be the most common real-world use of these trigonometric ratios I can think of. You got a building that you want to know the height of, that has a height of h, and then we have this angle. It's called angle of elevation, looking up the top of the building. So which trigonometric ratio are you going to use here? Tangent. So the tangent of 65 degrees is equal to our building's height over 340. So height is equal to 340 tangent 65 degrees. And you can just put that in your calculator and get that. You'll get 729.132 feet. And really, that's really all I intended to go over today. So it's just kind of a preview. We'll be doing a lot of exercise on that starting on Monday. Okay, good luck. And yes.